So 1 over n, and you take the summation, same, instead of this small xn, it will be capital Xk, and instead of this e to the power minus, because this guy goes to that side, it will be just e to the power I, 2 pi k small n divided by capital N. This is inverse DFT, okay? Quite similar, but not exactly similar. Okay. Just for you to know, maybe we can have an example of inverse DFT also. And these are the limitations of DFT. Like the main issue with the DFT implementation is it is not efficient if you have a signal with many data points, okay? Because it will take a long amount of time. You know why it takes a long amount of time? Because you are running through the full frequency and you are getting these three, like you saw these three, what you call that, bars. And again, these three bars are repeating again. So it is symmetric. You know it is symmetric, but you are still computing it. That is the main disadvantage. And if you get a small signal, this is okay. But if you have a very big signal with lot of sample points, then this gets very hard to do. Okay. I think we can do some examples. Yeah, maybe we can try some examples here. I think I have it. Consider that. Um, is it this one? I don't think. Yeah, I think it is this one. Yes. So let us see this function here. So this is a function to generate a simple 1D signal with different sampling rates. Okay, and we are using DFT in that. Okay, and signal here. Okay, so you can see like I have used one signal, that is amplitude is 3 and frequency is FREQ. Okay, what is frequency? What is the value of frequency? 1. Frec equal to 1. Okay, so it's 1. So 3, you can see it is 3 sine omega t, 3 sine 2 pi ft. Okay, we are plotting that, and there are 2000 sampling points. So you see 624 milliseconds only because it will be very less if you compute in a lab system, because lab system has around 2 times more cores than this. My laptop has around 6 cores, but no, sorry, it doesn't depend on the laptop only. It is collab, okay, and collab gives us very less computational power. Okay, we can request, but yeah, the basic. So if you run this in your lab computer, not on collab, but in your system or even in your laptop system, Python already installed, then this program will run even more faster. Okay, but you can get an idea that 624 milliseconds. Okay, 624 milliseconds. How I am getting it? You can use the time it thing in Python. Learn about this. If you want to know anything about how much coding time your program is taking, you can use time it. Okay. Here I have taken 2000 points. Let us take any ideas, 4000 maybe. So now it was 624 milliseconds for around 2000 points. Okay. Let us see if it is 4000, how much time it takes DFT. How much time DFT is taking. Oh, what happened? Hmm? Anyone seeing it? Why is the error? Okay, I think he will not recognize X. Ah, it will not recognize SR. Okay, maybe. Mhm. Maybe now. Anything undefined? Percentage indentation error. Indentation error. We can check. Great. Yeah, that was the error. Good. So you can see what is the time? Hmm. What happened? Oh, why it is not printing now? Anyone can debug this? This one? Uh-huh. You want this to be next line? Like this? Like this? Okay, we have to actually see how the DFT function looks, right? Hmm? No, DFT is defined here, right? Ah, okay. But still it was not running, I think. Yeah. Yeah. That's the issue actually. Because it depends on the previous one. So I have to run this one. Yeah, this is why I was saying I need X throughout. The same signal I need throughout the other programs. So I have to run each part. Yeah, because this guy is here, so I think it is creating some confusion, no? I think nothing is there, so I think it will run now. We'll do it previously as it is. But what happened? Ah, still not. Where? So last time also it was okay, no? Ah, now I think it is working because it is taking a lot of time. Okay, because we increased the number of points to around, yeah. Now you can see it is 9, yeah, good. 944 milliseconds. Okay. So 944 milliseconds. If you have around how many points? 4,000. Okay. So just note these values here, okay? So this is for DFT. This is for DFT. Hmm? So FFT will be even more faster. So yeah, that's what I was going to tell you. So if you increase the number of sample points, the time drastically increases. Time drastically increases. Okay. Although not doubling, here the points are doubling even if it is not doubling, but still it is on the increasing side. Okay. So therefore, there is a need to make the computational time less. Okay. So therefore, we will go to something known as a fast Fourier transform. Okay. So yeah. So this is what fast Fourier transform does. Uh, Maybe I can show it. Like there is a how you can understand. So you know that DFT has a symmetry, right? Was it clear that discrete Fourier transform had a symmetry? Yes, we saw it graphically, and you believed me, no? Yes, but we did not see depending on the expression. Yes, so just we'll see that. Anyway, so we covered this inverse transform also. Any issues? Any issues so far? Any questions you'd like to ask? Hmm? So there are two applications I have written down here. We will see that. But I think FFT is one such important concept here. After that, we will be ready, I think. Let me see which part I have to teach here. Uh, okay. So FFT, what FFT does? What FFT does? So FFT is actually computing DFT only. Okay. FFT, fast Fourier transform, actually computes DFT only. Okay. It doesn't compute FFT. Okay. FFT computes DFT. Okay. FFT, fast Fourier transform computes discrete Fourier transform in an efficient way. So there is nothing like compute FFT. Okay, FFT is another way of computing DFT. You are getting it? So let me write here. So FFT is an efficient way. FFT is an efficient way to compute DFT. Hmm? Fine. So actually, if you want to learn this in data structures, if you want to learn from a perspective of data structure point of view, what data structure does, it if you have an algorithm, data structures finds out what is the complexity of that algorithm. Okay, if you find an algorithm of order of n square, then you know it is of time consuming. Okay, and it is exactly the case of DFT. DFT, if you see the complexity, derive the complexity, it will come to be the order of n square. But when you apply the fast Fourier transform to the DFT, to compute DFT, it drastically reduces to n log n. Okay. Can you see that n log n has the complexity increased or decreased? What do you think? Yes, you already know log n should be less than n. Log n is always less than n. Take some examples. N equals to 2. What is log 2? When I was a kid, like studying in school, so what I usually do, I liked a lot of log functions. Log means something very nice, like powerful. Okay. So what I thought is, how log can I predict log? Then I'll become more powerful. So what I thought is, what is log 1? Suddenly it became 0. Then I got afraid. But log 2. Then I thought log 2, then if it is 2, then add 0 point and increase one value, 0.3 around. Check log 2, it will be around 0.3. Okay. So, no, order of n square. I did not go into detail why it is order of n square, but maybe you can check why it is order of n square. I just noted it down. Hmm. Bigo. This is Bigo notation. Bigo notation, I think it will come to your second semester. Data structures. Yeah. Data structures in algorithm. You will learn different types of algorithms. What is first in, first out? What is last in, first out? What is divide and conquer algorithms? I think data structure is really interesting. This is order, no? Yeah, yeah. One for loop inside where? Actually, if you see it in another way around, how many? Like you are seeing two kinds of multiplications here. Two kinds of multiplications here, okay, and you're adding those two multiplications. Maybe that is contributing to n square, because here there is a term of n, okay, like depends on n, and there is another quantity depending on n, and you are multiplying those two quantities, summing it up, okay. But if there was only xn, no exponential, then yeah, your valid point that it should be order of n. But as I see it's a multiplication of two quantities, then it gives me a feeling that it can be n square. It might be. I might be wrong. I did not look into it. But this is my version of seeing it. Like it can be. Maybe you can check and let us know next class. Hmm? Maybe class coordinator should remember. He will tell. Okay. So let us know. It is an interesting question. Hmm? So anyway, DFT is of order of n square, but fast Fourier transform will be of the order of n log n. That's what they found out. Others have found out. Okay. And you know log n is less than n. So therefore you can say n log n. n is positive, so it doesn't give me tensions. So n log n should be less than n square. So you can know that time has decreased, time has fallen. Okay, time has decreased. Fine. What is n? N is your size of the data considered. So you can see. Okay. So, and FFT has been widely used. This reduction of computation in time is significant, especially for big data. Especially for big data. Fine. So, yeah. Maybe I'll give you one assignment on DFT. That is known as the symmetries in DFT. Okay. Symmetries in DFT. You know already from the example in Python that DFT is symmetric. And due to that, it is not that computationally efficient. Hence, we move to fast Fourier transform, which will compute only from 0 to the nearest frequency. That is half of the frequency considered. Okay. So how we can show it mathematically that it is indeed true? One of you can ask me the question that maybe it is symmetric for that example. But how can you guarantee that it is symmetric for all? That is a good question, isn't it? So we have to show in general if it is true, isn't it? So let us see how can the symmetry in DFT can be thought of. Okay. So what is DFT definition? Can you tell? Xk equals to sum of small xn e to the power minus, no need to remember, you can look and tell. And you are going from n equal to 0 to n minus 1 number of terms, that is n samples, capital N samples. Fine. Okay with you? Now, I am asking you to compute xk plus capital N. What should it be? Just look into, maybe one careful visualization can boil it down, can reveal a lot of things. X, k plus capital N. Instead of k plus capital N, write the term and let me know what you are seeing. Okay. No. See, here it is k, right? Where k is appearing here only. So change there only. Nowhere else. So it will be n equal to 0 to n minus 1 xn e to the power I 2 pi. K is what? Instead of k, we now have k plus n. Isn't it? Agreed? K plus n multiplied by small n as usual. Everything is same. Just instead of k, we have k plus n. Okay. Now, due to this, what is happening to this summation? Lot of things will be simplified. Tell me. What will happen? Can you see that this guy, I can write it in terms of 2 pi kn by day n multiplied by e to the power I 2 pi n. Agreed? What can be this term? 1. Why it is 1? E to the power I theta, you know what is e to the power I theta? Cos theta plus I sin theta, isn't it? So e to the power minus I 2 pi n should be cos minus 2 pi n plus I sin minus 2 pi n. Fine. What is cos of minus 2 pi n? Cos of any multiple of 2 pi is always 1. Okay. And cos of minus x is cos x. Okay. So it is always 1. And I sin at even periodic point are always 0. Agreed? So it is 1. So what you are getting? You are getting n equals to 0 to n minus 1 xn e to the power I 2 pi k n divided by n. Okay. What is this? Xk plus capital N, right? And what is this guy? Do you see this guy before? He's our old friend. He's our old friend xk. Okay, so that's what is symmetric. If you take xk, any xk, the DFT, and add the number of sample points, then it is the same as the old xk. So this is the symmetric I am talking about. Symmetry in DFT. So now even more interesting things are there. Even more interesting things is there. See, I told you only one extension, x k plus 1 times n. Can you see that? xk plus n is nothing but xk plus 1 times n, isn't it? Agreed? What happens if you do xk plus 2 times n? Okay, x, this is k plus n, isn't it? Yes. So you know x, so let us call this as a k1, okay? xk1 plus n can be written. What is xk1 plus n? xk1 plus n, from here you know, right? From here you know that xk plus n is nothing but xk. Agreed? How many of you agreed? Yeah, many are there. Finish. I'll come to you. Xk plus n is equal to xk. Okay, you agreed with that, right? Now I am asking what should be xk1 plus n. Yes, xk1. What is k1? K1 is k plus n again. Now again, what is xk plus n? Xk. So what you got the idea? You got from this that x k plus 2n is nothing but xk again. You're seeing the folding and repeating thing, the logics. Okay. Now can you generalize this? Can you generalize this to xk plus I times n? I is an integer, positive integer. It will be just xk. Any integer. Because xk plus 2n is equals to xk. xk plus in is x. Try to show this. Try to prove this. Proof. Huh? Try to prove. Okay. Try to see it is always true. Hmm? So this is just the symmetry I wanted to talk. Yeah, I think now it is time to look into some applications. Uh, yeah, so I will tell you one example here. See this example. This is some from data set. Okay, we are applying a real data set into action here. Okay, what you see on this top here on this A part is the time, like the year. Okay, year 2019 to 2020. So 29/11/19 to 1st January 2020. Okay, and what you are plotting here is the amount of electricity. Okay, amount of electricity units consumed in that area. Okay, maybe you can consider Tirunelveli. Okay, so this is the time interval. Like this is the set of data you got. You can see it is very non-linear. Okay, non-linear, very non-linear data. Hmm? So this is what the electricity consumption. Okay, and what you do, you apply the discrete Fourier transform. You apply the discrete Fourier transform to this data. Okay, to understand more about this signal. Can you understand this signal? No. So you have to take help of discrete Fourier transform, which will boil this complex signal into a sum of sine and cosine, like fundamental signals, and more importantly, convert that signal into frequency domain. It will give you the important frequencies present inside the complex signal. So this is the complex signal. Complex looking, it doesn't mean that complex number. Complex looking signal. Okay, complex looking signal, and this is the DFT. More importantly, it's the FFT. Okay? It's the FFT, fast Fourier transform. And you can see that it doesn't have lot of peaks. And since we are doing a lot of intervals, this peak is hidden. This peak is hidden. So what we can do, zoom in this part. We can zoom in this part, isn't it? Just zoom in this part. If you zoom in this part, you will get this. You will get something in the below. Okay. So can you see the peaks more clearly now? You can see the peaks more clearly, isn't it? So where the peaks you see? Where are the peaks at 12, then 24, then yes, 84. Now these are the hours. These are the hours. Can you think that it is indeed true. The electricity consumption rises. So you see the peak means these are the electricity, right? The electricity units on the Y. So the electricity units, they rise up every 12 hours or every 24 hours or 84 hours. Okay, you sleep at 10 p.m. Okay, not usual. You sleep at late, but still, suppose you sleep at 10 p.m. Okay, sleep at 10 p.m. Then you actually start using the electricity. Most households they start using electricity after 12 hours around. Okay, hardly. Like you can imagine, like those people start the jobs at 10 or something. They will start using the toaster, start using the heater and everything at after 12 hours. So you can expect that there should be a peak after 12 hours. That is logical. And you actually see in the data also. The data from all the households, and they see that most of the households, the electricity unit spikes after every 12 hours. You got the idea how I'm interpreting from FFT, like the FFT data applied to the electricity units. Any doubts? You got a basic rough idea how the FFT can be used, no? I think this could have been a very nice project if someone could have taken to present. Remaining groups heartbeat has increased. But anyway, this is a good project to take up. Still, new research has been carried out in this, like how to take electricity data and apply FFT to denoise the data and also understand some concepts related to it, to gain more information about it. Because it is really important. Why you understand? Why it is really important? Because electricity data is a highly complex data, and many households randomly they are using. You don't know when they who is using. Yes, and suddenly if there is a solar flare, suddenly if there is a solar flare and you are continuously monitoring this FFT data, then suddenly from the normal previous spikes, due to the solar flare you will see a higher spike, okay, or maybe lower spike as lower than usual. So maybe there can be sudden blackouts. Maybe there can be sudden blackouts, isn't it, due to the solar flare? You get that in news, isn't it? How many of you heard that there will be a solar flare and there can be blackouts? How many of you have heard that kind of news? Okay, Google it. There was a recent prediction for India also. Anyway, uh, yeah. So just some motivation before we stop everything. So anytime a signal is processed, there is a good chance that a fast Fourier transform is involved. Okay. So if a signal is getting processed and it is getting processed very fast, then you know that there a Fourier transform is FFT is involved. And if the scientist would have discovered it sooner, it could have put a stop to the nuclear arm race. Okay, so many two different aspects. Okay, so he is, I think, a well-known YouTuber. I think Veritas. So you can get a lot of nice contents in his case. What is Fourier transform? Basically, like it is like discovering the hidden musical notes from a chaotic symphony. To just make a proper, motivating you to motivate you properly. So yeah, so you can see why we are actually doing it. Like you can see that it transforms a signal into its constituent frequencies. Okay, that's what Fourier transform does. And one of its crucial application is in audio denoising. Okay, you can denoise an audio where you have an unwanted noise, maybe in the background someone is speaking. Okay, and that can be isolated because that will come as a peak in your frequency domain when you do the FFT, and that part you can just remove. That part you can just remove, and the noise will be removed. That is so powerful. Okay, that is so powerful. So thanks to the Fourier transform's ability to unveil the underlying structure of signals, it's an indispensable tool in modern audio processing. So yeah, revealing the true essence of human speech and music. I think due to this only we are able to enjoy very nice music of say many musicians. Anyway, so just I have taken these from this Medium page. I just came across this Medium page. I Very nice resource. You can look into it. So this is the input audio signal. Audio signal looks like this. You have samples and the time. And what we do is the fast Fourier transform. You can see it has a lot of peaks, isn't it? It has a lot of peaks. This is the real data set. Instead of 1 to 3 peaks, you see a lot of peaks. Okay. What you do, this is a technique known as spectral gating, a common approach for cleaning audio files. Okay. What you do by selecting specific frequency components, you can remove the unwanted noise. Okay. So if you see that there is a high loud noise, then you can maybe remove this guy. You can remove this frequency which is responsible to produce that spike. Okay. Further, like you can see, now I'll ask you one thing. Which part of this image, this is an image, isn't it? And this is not that as not that of a good quality image. I am asking you which part you don't see, which part is not visible to you. Can you tell? Look carefully into this image. Hmm? Left hand side. Huh? Edge and corners. Good. Edge and corners are not visible. That's a remarkable visualization, observation. So, but which edge is needed to us usually? See, this is almost visible, like some potatoes or tomatoes are there. Okay, no worries. But if you see this part, it is most important, isn't it? Because there is July written, but what is the date is hiding here? July 13th or July 15th, 29th? We don't know. That is the noisy image. Okay, you can think till now FFT has been applied to one-dimensional signals, but this image is a two-dimensional signal. You have signal both on x and y axis. Okay, the data both on x and y axis. So it's a 2D signal. The image is a 2D signal. So you have to apply 2D FFT method, which we have not covered. Okay, 2D, just it is just an extension of 1D FFT. So you apply the FFT, this you will get. This you will get as the FFT data. Okay. So you, at least you know which part of the images are like, you have to take care of. Okay. So if you apply the inverse DFT and all, then give you this image. This is known as the denoised image. Can you see that this is a denoised image? Can you see that now? What is the date? July 13th. Like this was not clear before. This was not clear before, you see. Okay, this was not clear before. But if you apply this 2D FFT, it can denoise your image and can give you a good quality image. Okay? So yeah, it is full of projects. I missed it. I should have given this as a topic. But anyway, like at least you got some applications to know. Hmm? So this is all about DFT and FFT. Okay. Maybe. Uh, Wait. Just wait a bit. 5:30 now. So I just have some Python code I just want to show before leaving it out. Yeah. Um, yeah, you can see. No, I will not run the code. I will not take much of your time. But I just want to show to you that indeed FFT is very fast. Can you remember that when you did the DFT, discrete Fourier transform with the 2000 points, it took around 624 milliseconds. Okay. Now I'm taking around 2048 points. I'm taking 2048 points and I'm timing it up. And you see, I have written the FFT for this. FFT, okay? And you can see it took 44.5 milliseconds. So FFT, this is for DFT. And FFT is just 44. You can see it has decreased by 1/10th. Yes, like 90% decrease. 90% decrease of time. So that's how fast FFT is. And you can actually use SciPy okay, the functions FFT and IFFT. FFT is fast Fourier transform and IFFT is the inverse fast Fourier transform. These functions from SciPy, okay, and plot the results. Like how you can do it from SciPy.FFT pack. Yeah, there is a pack, FFT pack in Python. From that pack, you bring out FFT and IFFT. Okay, there you can bring it. So that's how it is. And if you want to perform FFT, what you have to do in Python? Just FFT, just like SVD data input. Similarly, FFT X. X you can give, you can see X are lot of these signals. X are lot of these signals, isn't it? And you are doing FFT X, that's it. That's it. Fine. So I'm plotting them up. So you can see that you are getting almost the same structure now. Okay, for this, what FFT does, FFT is showing only the required three frequencies. It is not showing the other part, which like DFT was doing, isn't it? So you can indeed see that this complicated signal has three peaks, three spikes, three peaks. Okay, each peak is giving you the frequency of the decomposed signal. Fine, fine. Okay. So and also very nice that it took only 6.45 second, I think. What second? Microsecond. Oh, wow, faster than this. It was milli, but it was micro. So quite fast. And yeah, I think some complicated. I think yeah, that's it. This is I think maybe just 1 minute. I don't remember this guy. Hmm? What happened to Miss Durga? Like you will separate it totally. Okay, so we learned the electricity example, no? So yeah, mm, there is something known as filtering. Shall we read out? No, just a tiny concept. Or how many of you want to continue the tiny concept of filtering, or you want to stop? Huh? Next class maybe. Huh? It will just take around 15 to 20 minutes. That's it. Hmm? Next, okay. Okay, so next class, as you know, when will be the next class?